Welcome to VLSI Lab. So, last semester you have studied about VLSI, and in this semester you will be dealing with VLSI Lab. Alright, now in this lab there will be two sections. Okay, first section is analog and the second section is digital. Okay, so you will be designing in both. So in this lab you will be designing, or as you say, the experiments that you're going to deal with. Okay, so analog domain design will be there and digital domain design will be there. Alright, now in order to get these experiments done, the software or the tool that you require is Cadence. The software is Cadence. Okay, so now this Cadence tool provides platforms for both analog domain and digital domain. Okay, it provides platforms for both kind of designing purpose. Okay, now the tool, this is the software. Okay, this is the software. Cadence is our software. Okay, this software provides platforms for both analog and digital domain design. Okay, now the tool required for analog domain is Virtuoso. Okay, is Virtuoso. Alright, now in this Virtuoso there is different stages of designing. There are different stages of designing. So in the first stage, okay, what you are going to do, you are going to make the circuit. Next stage, you are going to make the symbol for the circuit. So in step 1, where you have designed or you have made your circuit, okay, where you have designed your circuit, in the next step you are going to design a symbol for the same circuit. Okay, and in the third step what you are going to do is you are going to test the symbol. You are going to test the symbol by making a test circuit. Okay, understood? After these three, then you will be doing simulation. Okay, so this simulation will give you some results, and then you will be doing, underneath this simulation you will be analyzing the results. Alright, so these things form your tool flow of Virtuoso. Alright, in digital domain, okay, in digital domain the main thing over here is that you're going to do coding. Now, which programming language will you be using for coding in electronics? And you have already covered that in 5th sem, is Verilog HDL. Is Verilog HDL. But like in your 5th sem in HDL lab, you were dealing with Xilinx IC. The tool name of that software was IC and the company name is Xilinx. Alright, so over here you're not going to use IC tool. The tool provided by Cadence for digital domain are 3. First tool, incisive. Okay. Second tool, encounter RTL compiler, and third tool is encounter. But according to your syllabus, the third tool is not required. So you are going to deal with 2 tools under digital, that is incisive, and the second one is encounter RTL compiler. Okay, so under this kind of design, digital design, obviously if it is relating to code, that means you will be writing the code and its test bench in Verilog HDL. Okay. After writing the code and test bench, what do you do? Normally when you are dealing with any coding related lab, what do you do after that? You do functional simulation. Okay. From here you will be getting some graphs or results. Alright. Then after this, what we will do is we will be doing what? After getting the functional simulation and the graphs and result, when we realize that yes, this is what we wanted to code for and this is the result that matches with it, right? So let's suppose I wanted to make a pen and after coding for it I am getting a pen, that means it is correct. Okay. After that, what we are going to do? We are going to generate reports. We are going to generate reports. That means what kind of reports? In VLSI, you do remember that we used to go for tap parameters. T stands for timing, A stands for area, and P stands for power. So in this stage, we are going to generate timing, area, and power reports of the device that was designed. Now over here, after doing this and finding out that yes, it is correct, that means I have already designed a device. Okay. After designing this device, what we are going to do? We are going to generate reports. What kind of reports? Reports relating to timing, area, power. That means if this is the device I have designed, how much delay does this device have? How much area and how much power does this device consume? Okay, I want to know because I am designing something. Alright. Now, let's suppose I am getting some values. And I don't like that values. Okay, I want to make it better, or I want to optimize my design. So what I will do, I will add some constraints. I'll add some constraints. What are constraints? As the name suggests, you are adding some hurdles, right? So I will add some constraints and again generate the tap reports. After adding the constraint and generating the tap reports, this is our final goal. This tap report is our final goal, and this is what we want. Okay, we don't want any unconstrained value. Why? The question is, why can't this be our final value? Why do we have to get this, then add constraints, and then again generate the tap reports? That is because if anything is unconstrained, that is not a good design. What do you mean by unconstrained then? If something is out of bounds, something is out of control, you have no power whatsoever on that device, then you never know when it is going to work and when it is not going to work. Is it a good design from a designer's point of view? No. Let's suppose you are the customer and I am the one manufacturing a pen. Okay? I am manufacturing this pen. Now, I have manufactured it and you have bought my pen. Now, this pen will write sometimes, this pen will not write sometimes, according to its will and wish. Would you continue with this pen? Of course not. Would you continue with my company? Of course not. You will go for some other company which provides reliable pens. Similarly, in the world of electronics, let's suppose you are buying a phone. Okay, let's suppose you are buying a phone and all of a sudden that phone stopped working. You thought something happened, something out of your fault. Then suddenly it starts working, then suddenly it will not. So it is unbounded, right? Unruly. Would you like it? Of course not. That is why whenever engineers in the field of VLSI, they design a product or design a device, they don't want it to be unconstrained, and that is why we add the constraints file. After adding this constraints file, whatever tap reports I am generating, that is my goal. That is my goal. Now, one thing to remember over here is that there is always a trade-off between the tap parameters. What is the meaning of this statement? Trade-off between the tap parameters. It means that if I am reducing delay, see, I am writing delay, but T is for timing. Timing is nothing but delay. How much time does this app take to open? That is the delay. Time is nothing but delay. If it is high speed application, high speed device means what? Delay is less. Okay? High speed device means delay is less. Alright? Timing is delay. So, if I reduce the delay, okay? Let's suppose this is one device, okay? Let's suppose this is a device I have manufactured. This device has a specific function, okay? Now, this device takes 0.01 nanoseconds to start working. Okay, it takes 0.01 nanoseconds time to start working. So that is the delay. Let's suppose I don't like that delay. Okay, so I will try and reduce this delay. Now I have made the delay as 0.001. Okay, I have made the delay as 0.001. So if I am going to reduce the delay, it might so happen that area might increase, power might increase if I am reducing delay. That is the statement of trade-off. That means, what is our goal? That there should be an optimum balance between the three. Okay? It shouldn't be, the delay is very, very less, but the power dissipation of the product is too high. If that happens, would you like it? Do you like when your device gets heated up? Do you like your phone getting heated up after a continuous use? No, you don't like it. That is another thing, right? So, what is the target of a designer? That there should be a balance between the three. Okay? There should be a balance between the three. So, now here I will get some values. After adding constraints, I will get some values. So, what is happening is, after you get these two set of reports, what you have to do is, you have to analyze the difference between the two set of reports. Okay, so here in analog, what you are doing, you are analyzing the results. Here in digital, what you are doing, you are analyzing the difference in the two sets of generated reports. All right, understood? So this is what we are doing in Cadence in both the parts. Now, I said the tools in digital are incisive and encounter RTL compiler, that will be of your use. But here nowhere have I mentioned both of them. If two tools I am using, that means I need to know which one is where. Till this part, coding, test bench, functional simulation and graphs will be taken care by incisive. Okay. After this, whatever reports and stuff you have done so far over here, this will be taken care by encounter RTL compiler. This will be taken care by the tool encounter RTL compiler. All right, understood? So now, why Cadence? Why Cadence? Why didn't we go for any other tool apart from this? As we have already covered in HDL lab, we have used ISE, isn't it? We used ISE. There also we did our coding. There also we wrote our test bench, and we got the graphs also. Then what is the need of Cadence? Analog part, any other software, Proteus, everything, they are there for analog design. Then why are we going with Cadence? Because Cadence is a research software. Cadence is a research software. Okay? That means it is not a drag and drop software. You remember in some softwares, what did you do? You just selected the device you want for your circuit. You dragged it from the palette into that editor screen, and you interconnected and you got a result. That is a drag and drop software. You can't edit the device that you have dropped. Okay? You cannot make any changes. You cannot analyze the result. You cannot generate tap reports. So, because Cadence provides us with these points, where you can do analysis and you can optimize, where you can generate tap parameters and you can optimize, these things are only possible via a research software. So all the research scholars actually are using Cadence for VLSI design. Okay. Now, Cadence is for scholars, okay, PhD scholars, MTech scholars, researchers in this field. They use Cadence. All right. So, Cadence provides 3 technology files. Cadence provides 3 technology files. First is 180 nanometer, second is 90 nanometer, and third is 45 nanometer. Okay. 180 nanometer, 90 nanometer, 45 nanometer. The question is now, what is this technology file? The question is, what is this technology file all about? What were the variations? 180 nanometer, 90 nanometer and 45 nanometer. Okay. You remember VLSI module 1, we studied about MOSFET. In that MOSFET, we studied about two parameters that actually balanced or actually played a major role in controlling and deciding what should be the output of that MOSFET. That is channel length and channel width. Channel length and channel width. Remember the MOSFET structure? This was our channel, N plus, N plus. Now this was our oxide layer. On top of it I have the gate, and this side is drain, this side is source, and we had a body terminal, and the substrate was p-type. So what kind of MOSFET have I drawn here over here? It is an NMOS. It is an NMOS. So this channel length is the distance between source and drain. The distance between my home but if I stay really close to the college, it will take me lesser time, right? So lesser the channel length, better the or faster the response, right? So this channel length is nothing but the technology file. All these things were covered in 6M. Okay. So this channel length is nothing but the technology file. So these values that are written, that means what? If I am choosing 180 nanometer, okay, if I am choosing 180 nanometer, this will imply that the channel length of all my MOSFETs are 180 nanometer. If I am using the 90 nanometer library, that means all the MOSFETs channel length are 90 nanometer. Similarly, for 45 nanometer as well. I am saying all the MOSFETs, that means NMOS or PMOS. Both are MOSFETs, right? So, if I'm, now all these things are library. If I am choosing 180 nanometer, in between I cannot add a MOSFET having 90 nanometer channel length. Not possible, not allowed. So if I am working in 180 nanometer, all the MOSFETs should be of this library. Okay. So the library files provided by Cadence are GPDK 180, GPDK 090 and GPDK 045. GPDK 180 for 180 nanometer library, 090 for 90 nanometer library and 045 for 45 nanometer library. Okay? Understood? Now, this GPDK indicates this term, okay? This term indicates that these files are generic in nature. Generic means what? That the results obtained are an estimation. Okay? Means useful for research purpose. useful for research purpose. Okay. Now, if it is an estimated value, useful for research value, then what about the companies that are working in VLSI? Can they be working in GPD? Can they even work with these files, GPDK files? Absolutely not. Absolutely not. So, the industry people uses the files TSMC, Taiwan Semiconductor Corporation. Okay. So, you can find out 028 means 28 nanometer. Okay. Like that. They work in TSMC files. But we, since we are academicians, we are researchers, we will be dealing with GPDK files. Why? Because an estimated value is also good enough for research purpose. Now this estimation value, don't think that the accurate value should be 99, but estimation I am getting 90. No. If the accurate value is 99, you will be getting 98.9999999. That is an estimation value in Cadence. It is very, very close to accuracy. Okay, it is very, very close to accuracy. Okay. So this is the introduction of the tool that you are going to deal with. This is the introduction of the software and the tools you are going to deal with. So what are the tools you are going to deal with in this semester? Virtuoso for analog, Incisive and Encounter RTL compiler for digital. Okay. Now, first we will be dealing with analog designs. Second, we will be dealing with digital designs. So first analog, then digital. We'll finish off all the analog experiments and then we will be going for the digital design. Okay. So the first experiment in analog. And one more thing to remember is that analog design, I'll be using Virtuoso and the library file will be GPDK 180. We are not going to use 90 or 45 for our syllabus. It is 180. Okay. The first experiment is inverter. So, this was the circuit, right? PMOS on the top, NMOS at the bottom. Clubbed gate terminals provided the input. Clubbed drain terminals provided the output. Body of PMOS connected to VDD. Body of NMOS connected to ground. This was our circuit that we studied in VLSI. Now, instead of calling this a circuit, in Cadence what you will be calling it as a schematic. So, the first step over here, make the circuit. It is actually make the schematic. Okay, you will be calling it a schematic. Okay. So, what we will do, we will select PMOS, NMOS and then we will make the interconnections as per this schematic on the editor screen. So, first step is done. Second step, what was it? Creation of a symbol. So, now in Cadence, the dummy symbol is a square box or a rectangular box. Okay. But you have the option of editing that and making it as per the logic gate you have seen so far in your lifetime. Choice is yours. Doesn't really matter in Cadence. Either you go with the inverter symbol, the actual symbol, or you go with the dummy one that is being provided by Cadence. How many inputs are there? In one input, one output. So, let this be V in, let this be V out. So, V in V out. Okay. Am I done with it? No. Why? Because VDD is another pin and ground is another pin. So VDD and ground. Look at this symbol. There is no connection made. It is just a structure. The body and the pins in the schematic. Now the number of pins you add in your schematic, that many number of pins will be present in your symbol also. That has to be maintained. If it misses out, there will be an error. There will be an error. Next step. Once I am done with this symbol, once I have generated the symbol from the schematic, remember this, generate symbol from schematic. Okay, generate symbol from schematic. So now this that I have done, since I have generated from the schematic, internally both of them are connected. Internally both of them are connected. This is because we are using Cadence. So the third step was what? Testing the symbol. So let's suppose this is the symbol that we designed. So V in, VDD, V out and ground. This is the pins. Testing the circuit means what? Testing the symbol means what? If you want to test something, you need to give some proper voltages. So in Vn, what we will do? We will give a proper voltage source. Note, this is a pulse. So this voltage source is V pulse. I am using the actual name of the voltage source present in Cadence. Okay, so I need a pulse wave. Okay. Now for ground, I need to connect it with a ground terminal. So this is the ground component provided by Cadence. Okay. For VDD, VDD is what? Power supply. If it is a power supply, another voltage source is required. Can I give a pulse wave to that? Can I give a pulse wave to that? No. Why? Because pulse wave means once it is high, once it is low. If it is a power supply, that means I have to give a constant power, right? So the constant power over here is this. The name of this is VDC. DC voltage I am giving, constant voltage, right? And you have the option of giving the value over here. So normally in VLSI, we don't use 3.3 or 5 or 9 or 12 that you are accustomed to in your analog and digital labs. In VLSI, the power supply should be 1.8 or 2.5. So I like to stick with 1.8 volts. Okay. Now, in Vout, this is where I will take the output from. So can I add a voltage source? Obviously not. So what I will do, I will attach one capacitor and I will add an output pin. Okay, and I'll name this output pin as Vout. I'll name this output pin as Vout. Why did I attach a capacitor at the output? Because any circuit in VLSI should not be designed without a load. It should not be designed without a load. So this acts as my load. Okay, understood? So this whole circuit wherein your symbol has been given by proper voltage sources and a capacitor at the output, this whole thing is called as the test circuit. This whole thing is called the test circuit. Okay. So this is what you're going to do in VLSI lab. Alright. Next, after this realization, you will get some results that we need to analyze. So now this will be taken care in the next lab. Okay. wherein I will show you the whole tool and I will give the steps. So in our next lab, we are going to design this inverter. I have just given the flow of the experiment. I didn't say how to design. There has to be the designing part as well. Okay. So we will design this inverter, generate the symbol from the schematic, get the test circuit, test it, get the results, analyze it, and via doing so we will get to know the steps involved as well. Okay, so the first lab is always the introductory lab, and then in the next lab we are going to start with the inverter design. So this is all for today. Next week we are going to design inverter. Thank you.